Hi everybody and welcome back. This is the Control Engineering Geek. Throughout this series of videos, I am going to explain the model Predictive Control or MPC in detail. This includes different formulations of the MPC, solving the MPC problem, the associated stability problem, tuning the involved parameters, the robustness of MPC as a controller, and some other related subjects. Of course, there will be Matlab scripts for the most of the addressed subjects. The current video talks about the first part, which is the receding horizon. Let's jump into the subject. It is important to note that most of the materials that are presented in this series of videos are borrowed from the great book, Predictive Control with Constraints, which is written by J.M. So, what is the receding horizon that the predictive control relays on? The figure illustrates the idea behind that. Let us assume that we have a discrete time setting and k is the current time. At current time k, the output of the process is y of k. One can see the previous output history of the process from the figure, which is y of t. S of t is the set point trajectory. The output of the process should follow this trajectory, which is desired by the designer or the processor. R of t at k is the reference trajectory. One has to distinguish it from the set point trajectory. R of t at k starts at the current process output y of k and defines the ideal trajectory for the process to follow to approach the desired set point S of t after, say, a disturbance. The process should be turned to S of t as quick as possible. For that, it is usually assumed that the reference trajectory approaches the set point exponentially. Let us assume that the time constant for this approaching is t sub ref, which illustrates the response speed. Now let us see how this helps us to define the reference trajectory at current given process output k. Let the current difference between the set point S of k and the process output y of k be given as. Then, one can choose the reference trajectory in a way such that the error epsilon I step ahead be as shown, of course by assuming that process output follows it. Or as where t sub s is the sampling time. Sure, gamma should be between 0 and 1. Thus, the reference trajectory for I steps ahead defined as, or simply as. One can easily notice that R of k plus I at k depends on the given conditions at current time k. One can also define different reference trajectories, such a straight line from the process current time that can meet the set point after a pre-specified time. Now let me explain the receding horizon mechanism. This diagram simplifies the MPC control procedure. There is a model of the process in the heart of the predictive controller. Starting from the current time k, the controller utilizes this model to predict the future of the process over some horizon. The predicted future behaviors requires the input trajectory you have a plus I at k, where I evolves from 0 to defined control horizon. This input trajectory is assumed to be applied over the horizon HP. Now, the idea is to compute this control trajectory in a way desired scenario is achieved, such as a best predicted behavior. This will be explained in more detail when you are introduced to the optimization problem. Usually, a linear model is assumed of the controlled process as it is easier to deal with. We have used the notation u hat instead of u just to add at time k, we only have the prediction of the input trajectory along the horizon. This means that the actual input trajectory at time k plus I will be probably different. Another important point to be stated that the process output at time k is available when attempting to decide the applied control action. This means that the internal model has to be strictly proper, that is y of k depends on the past values of the inputs and not on the current input value u of k. As we presented all required definitions, Now we can introduce the whole picture of the receding horizon. The followings portray the big idea. First, examine carefully. We have past and future. Present is represented by the discrete time index k. The red line is the reference trajectory, whereas the dark yellow line is the predicted output based on the current output of the process. The light yellow line represents the measured output in past. For the control actions, we have the blue line, which is the past applied inputs, while the green bluey line is the future predicted, or more precisely, the computed control sequence. Now let us see how the receding horizon technique functions. First, we have a horizon along which we compute the future control sequence. From this sequence, we inject the first control action into the process. This produces a new output for the process. We move the prediction horizon one step ahead and use the output we had from last sample to compute a new control action sequence along the horizon. This predicted control sequence gives a corresponding process predicted output, as you can see by the orange line. Once again, we inject the first element in the new computed control sequence into the process, which again produces the new output as seen by the light yellow line. Following the same procedure, that is, using the new process output to compute a new control sequence and then apply the first control action into this, the process can approach the desired set point. Of course, given that there is no disturbances that may push the output away from the set point. This is the main idea of the receding horizon. In the next video, I will explain some simple ways to compute the control action sequences during the receding horizon fashion, along with some simple examples, so stay tuned. Thanks for watching this video, and please do not forget to hit the subscribe button.